Good afternoon. I'm Jan Delfs from DLR in Germany, and I'm the chair of the CES Aeroacoustic Specialist Committee, which is the European counterpart of the AIAA Aeroacoustics Technical Committee. This is the CES Awards session, but before we go on, we thought it is just too tempting having you gathered here not to make two announcements for upcoming events, and that's what I would like to do now, and ask our next chair of the next conference in Brussels, Christoph Schramm, to make us a little bit familiar with that event next year.
Thank you very much, Jan. Very nice being here. Let me try to see if I can retrieve my presentation. Should be here. Right, wonderful. So thank you for being here. So it's my true pleasure to invite you in 1 year from now, actually a little bit less, to come to Brussels. So it's in Brussels that we'll have the Aeroacoustic conference in 2026. It will be the first time ever that it's organized in Belgium. So it will be organized in collaboration between the Von Karman Institute, who will be the prime organizer of the event, and the Vrije Universiteit Brussels, which is the University of Brussels Flemish side, because for those of you who know the Belgian situation, there's always a Walloon side and a Flemish side. Otherwise, it would be too easy. So Brussels, so just to localize a little bit, so we are just around the corner here, right? And then if you pass the corner, and then you arrive in Brussels. So it's not too far. It's literally around the corner. So Brussels is a capital. It's the capital of Belgium, of course. It's the capital of Flanders, but that's another story. It's also the capital of Europe, so that might be one reason to visit Brussels. So Brussels is known for its institutions, of course. We have the European Parliament that is shared with Strasbourg. We have the European Commission, or a Holy Saint Mother, the Commission, funding when they want our research in aeroacoustics. You might want to come to Brussels for other reasons, for its Gothic flamboyant style. The Grand Place of Brussels is famous for this. You might want to come to Brussels for its cartoon and comic strips, so it's also the capital of comic strips. It's also the world and universe best place for chocolate, obviously, even though half of the production is made by Italians and Swiss people, but okay, it's still made in Brussels. You might like French fries, so the French invented the French fries, then we explain to them how to cook them, and eventually we know that the true reason why you might want to come to Brussels is more this one, which leads me naturally to one of the most visited monuments in Brussels that you might know, the mannequin piece. So that's our most impressive feat in Brussels. Now, jokes apart, there are other good reasons to come, is the conference. So a couple of dates. The conference will take place between the 26th and the 29th of May. It will be on the campus of UB, as I mentioned. Dates have been fixed already for the welcome reception and gala dinner. The abstract submissions will start on 15th of September, so relatively soon, and until 15th of November, and then you see the other dates. The key date is for the early bird registration deadline, of course, and then we have a date that I will insist on later, is the sponsors deadline, and I will probably come to see a couple of you to ask for some money at some point, or if you know somebody who has some money, to help us to sponsor the conference. So it's a fairly nice, so it's a very nice campus. It's a very green campus. It's very close to the downtown part of Brussels. We have one plenary room that can host up to 1,000 participants, so invite friends. We have 11 breakout rooms, but we could have more, one exhibition space, restaurant, and all the facilities that will come. Last slide. Don't hesitate to visit us on our website, aeroacoustics2026.eu, and you can also follow us on LinkedIn for the more news about, for example, if you wonder about this silhouette. In here, there will be some news to explain what this is. It was a multicopter before multicopters were invented, and that was Belgian. So thank you very much, and hope to see you all there in 1 year from now. Thank you. And Jan, I think you have your, yeah, I'll let you.
Thanks, Christoph. Thank you. You may know that on an annual basis, in each fall of every year, we in the CES organize workshops, thematic aeroacoustic workshops in Europe, and I would like to draw your attention to the next workshop we have for this year in the Netherlands on advances on rotor and propeller noise prediction, mitigation, and future challenges, which will happen in 21st and 22nd of October, and you can hand in abstracts until the 9th of September. You're very welcome and very much invited to take part in this workshop. So that was the advertisement part, and let's then go on with our award session. The first thing I want to say is I would also, on behalf of the CES committee, I would like to thank the staff of AIAA very much for setting up this conference. And in particular, I want to thank the chairs of the 31st Joint AIAA CES Aeroacoustics Conference for their work to set up this conference. In particular, I want to acknowledge and thank Nathan for his work. It takes a lot of efforts. It takes very much dedication to set up such an event, and I can only say very many thanks, Nathan, for this organization. I'm very pleased and I'm very honored to chair this session, which is the CES Aeroacoustics Award session. In fact, I'm only a substitute for Daniel Juvet, who is the chair of the awards subcommittee in CES. This is, I think it's a very important, it's a very special session, and it is important because we honor a personality with outstanding achievements in our exciting field of aeroacoustics. I'm very happy that so many of us have gathered here, the small worldwide community of aeroacousticians, and to be part of this event here, which we could even call a kind of a celebration. So with this, I would like to say a few words about the award itself. Daniel asked me to do so. Okay, let's see whether that works. Oh, no. Okay, yeah. The CES Aeroacoustics Award was established in 1998. And it is bestowed on a yearly basis. We have one member per CES country, and the nomination is a two-stage process. The first stage is open to the whole aeroacoustics community, an open call, and the second stage is then a review of candidates on a short list. And then there will be several criteria for ranking those candidates. That's the way in which it's done. This is a list. This is a list of former recipients of this award since it was established. And next time we will sit here, we'll be in Brussels, and then there will be one additional name on that list. And this additional name you see here is Phillip Joseph from ISVR in the UK. And with this, I would like to ask Phil to come up to the stage so I can present the award to him. Next, I would like to ask Chaitanya Paruchuri to give a small laudation speech for our candidate. I put this away and you can do that.
I think it's already open.
I see.
Thank you, Jan. I'm Chaitanya Paruchuri. I'm from ISVR, University of Southampton. It's my pleasure to introduce Phil today on this occasion. So, before I go into a formal introduction, I would like to start with 3 things about Phil. I want to quote his own words to what he usually says to all his students. So the first thing is, it's really not a job we do here. Someone is paying us to talk to students and do research. So this shows how much he loves his job, and he has an open door policy and is very kind and an empathetic supervisor and a colleague to every one of us. And the second thing what he says is, love the equations and they will never upset you. To be honest, I don't know, some of you all might be still waiting an email from him or must have ignored from him. I mean, that's a classic Phil. So people, usually don't reply much. That's a classic Phil. But I would like to say that he's really hands-on with his research. Example, I want to tell one example of last summer. So he has just got one idea. He just formulated, did all his math, and did its coding, validated experimentally, and wrote the paper within 2-3 months, which is really impressive to all of our students. So it's really hands-on with his own research. And the third thing about him is, take it easy. We are not finding a cure for cancer. So again, this is not to say about the field, not to belittle the field of aeroacoustics, but this is to say that he has a very healthy work-life balance, and he encourages all his students and colleagues to have the same, says that life is too short and we need to do what we love doing it. So these are 3 things which I want to introduce Phil, and I'll go with a formal introduction, but this will set a stage what kind of person he is. Okay, growing up, Phil was grown up in the East End of London, and which is called Bow, which is in the east side of the London it is. And it's the Eastern charm, which are the people over there are very approachable and always with good sense of humor. And he's definitely one of them. And the East End is famous for EastEnders, Jack of Rippers, and Cockney, which is very close to Indian accent, but it's not, I don't think so it's close. and it has a rich cultural diversity, and it's one of the poorer areas in England, especially the east side of London. And this is Phil in 1970s. And he's the only student from his class to complete and move towards undergraduate studies. And he did his Bachelor of Science in Physics in 1984 from University of York. And later he has moved to ISVR for his master's in 1985. And his project is measuring sound intensity in flow. And that's the only picture you can see Phil with a perfect hair. Okay. So, and that's in 1985, it's 40 years back, that is. And later on, Phil did his PhD in active noise control at ISVR in 1990, where he did some theoretical and experimental work on active noise control in an enclosed sound fields, and where basically the goal is to have this secondary loudspeaker to be able to cancel the primary field at any given point in space. So it's a more analytical and also experimental validation. He did some in his PhD time. And his own supervisors was Steve Elliott and Phil Nelson. And his own words, they say that it is pleasure to supervise Phil's PhD, to which he brought a mixture of rigor, skepticism, and humor. And the second supervisor, who is Phil Nelson, is also a big name in the field, who says a very talented scientist, a great personality, and a wonderful sense of humor. So everybody says it's sense of humor. About his sense of humor. Let's see that in his talk. Okay, and after the PhD, he moved to Australia, where he did his as a research scientist in 1991 to 1994. And that time frame, he has lost his 20% of his hair, and that's Phil over there, if you see here. Okay, and then he worked on problems of shallow water acoustic propagation and reverberation monitoring, and then followed with the research fellow position in active noise control, where he extended his PhD to include the effect of mean flow, and followed it, he has taken a research lectureship position in shallow water acoustics from 1996 to 1999. And later in Aeroacoustics, in 1999, there's a collaboration between Rolls-Royce and University of Southampton. There was a Rolls-Royce UTC established, and he was acting like a deputy director in 1999. So he took up a role of lecturer in acoustics in 1999 to 2001, followed with a senior lectureship and with a professor of acoustics in 2008. So in the last 25 years, he worked in aeroacoustics, and broadly I can classify the whole the contribution in three main categories. The first one is characterizing the ducted fan broadband noise by developing measurement techniques. And second one is the theoretical source modeling for fan broadband noise. And third is a passive active control of noise. So I'll be focusing more on the first bit, and the other two I'll make it a quick summary of it. The first thing is on characterizing ducted fan broadband noise. So he has developed theoretical expressions for sound radiation from a single incident duct mode, arriving at an open end of a semi-infinite circular unfranched duct over here. So basically, you got to know the ratio of power transmitted to the far field and also the incident modal power. And his work is published in 1999 on multimode radiation from an unflanched semi-infinite circular duct. And later he extended this work to include the effect of mean flow, and this is a far field activity. And this is a far field activity if any incident field which is impinging onto the end, and that's a far field activity of the sound. And he published the work of multi-mode sound transmission in ducts with flow in 2003. And followed from this theory, he moved on to develop some measurement techniques, where basically he applied this theory and to estimate the far field directivity using an induct linear microphone array at this point. So using this induct array, how can we get the far field noise? And there's a paper published in 2010 on this, using his theory developed. And later on, he moved towards estimating the modal content and the source trends by developing a two inverse methods. Example, if we have some array of microphones in duct or array of microphones in the near field sensors, and how can you predict the modal content and strength of the broadband noise sources? And this work has been published in 2006 and 2007 as well. And followed more recently, in terms of measurement techniques. He has a two microphone method he has developed to able to get back the modal amplitude distribution of the mode, and also use this technique to extend it to a one ring microphone method, especially in the intrastage region between the fan and OGV, so able to separate out the dominant noise, so which is in this case the OGV compared to the fan. And this work is done by 2017 and 2023. And the second phase of work, I'll quickly go through it. It's on developing the theoretical source models for predicting the fan broadband noise, where there is a lively debate between academics and Rolls-Royce between how useful are these flat plate models, and he took it up and he understand and modeled the fan broadband noise sources, especially the turbulence cascade interaction noise and the trailing edge noise sources and the interaction noise sources. There are multiple analytical model work he has done, and this is a team of people in ISVR, and it's a crucial time where he lost his 30 to 70% of hair while developing these analytical models in one decade, in 10 years time frame. And later he has been the UK's first university-level anechoic wind tunnel, and it's called DARP. This is in 2005, 2006. And he used this facility to understand on airfoil noise mechanisms and also develop some low noise technologies like on leading and trailing edges. And not only that, he developed the worst, scariest low noise airfoil, which is the trailing edge serrations there. It's looked like a weapon there. That's the first trailing edge serration design. It is around 2005, 2006 time frame. And I just want to show that, which is tested in the DARP tunnel. And let's move on to what can we say about Phil as a person. Let's quote some of the what his own students say about him. The first one is he has welcomed many people to feel to feel home in UK, especially myself and a lot of young people like me. And few people say he's one of the kindest human beings I ever worked with. And also there are memes between the colleagues and friends. And they say that don't look back in anger, look back smiling like Phil. So that's a meme we all do. So usually it says what kind of person, what kind of character it is. And also he says that we only need few good papers in our career. Papers should be like tones, not like broadband noise. So basically he works on broadband noise, but what he always insists to academics is to publish some good quality tones, like good quality papers, at least one a year or something like that. That's what matters. And coming, because we all love him, so what kind of gifts we give him to thank him? So sometimes we make him person of the year, and which he loved being that. And also sometimes we make a meme to Phil is dating Kylie. So these are all the gifts. He cherished them and keep them with him. And Phil is a kid at heart, definitely, and also a kid magnet, actually. To be honest, this is a picture of an ISVR Christmas party. If you're wondering where is Phil, this is Phil. He has hair grown temporarily. He's an ISVR Christmas Santa there. And that's picture for my daughter's birthday. He loves playing with kids. And if you see these pictures, so he's a kid's magnet. So in summary, I would like to join us to congratulate Phil for all his outstanding contributions to Aeroacoustics. And thanks for all the humor and kindness with all of us. Thanks a lot, Phil.
Thank you very much, Chaitanya. And with this, I would ask Phil to step up here and give his awards lecture. Just have to find it, that's all. Oh, it's many. Which one is it? It's this one?
Well, thank you very much for coming. It really, really does mean a lot. I did have a few thank yous to give, but I hear that I have a few minutes on Wednesday, so I'm going to leave my thanks and acknowledgements to everybody on Wednesday, if that's okay. But it is a huge honor, and I'm incredibly humbled to receive this award, so thank you. And I'm afraid my talk is going to be a real anticlimax after Chaitanya's presentation about me, but I'll do my best. So when I heard that I was going to give this talk, I thought really hard about what I could give. And I thought, rather than talk about one particular subject in detail, it might be good to talk about a few subjects that have got a common theme. And then I looked back over the kind of 25 years or so to think about what connects some of the work that I've been doing. And I thought it's probably the whole concept of destructive interference, where you introduce a wave superimposed onto another wave, but with an appropriate phase relationship to reduce the pressure level. Superposition with the idea of destructive interference. So what I'm going to do in this lecture in the next 45, 50 minutes is just go through some 4 or 5 scenarios, and they're all quite different, that uses destructive interference to reduce the noise. So hopefully this will be interesting. Hopefully. So the first problem that I want to consider is the idea of trying to minimize or reduce the sound power output of a single monopole source situated into a mean flow. So you can kind of see the situation here. There's a point source located at XP in a uniform mean flow. And what we want to do here is to introduce another monopole source located very close to it, a distance d. And you can see that it's located at an angle theta relative to the uniform mean flow. And what we want to do is to drive that secondary source to minimize the total sound power radiation. And you can see there that these sources are at a single frequency. So before we do any of the minimization, we need to understand the nature and characteristics of sound propagation from a single point monopole and a uniform flow. And it turns out to be a lot easier to formulate this problem in terms of velocity potential rather than pressure. And once you have the velocity potential, it's fairly straightforward to compute the pressure or velocity by a time or a spatial derivative, respectively. So we're going to do this, solve this in terms of velocity potential with a view to minimizing the power. And so what we have to do is to solve this forced convected wave equation. And on the right, what you see is a fluctuating monopole volume velocity. But the point is that it's a point source. It's a singularity. So the point source only exists at a single point, XP, and is zero everywhere else. And that's a useful idealization because the point source obviously doesn't affect the uniform flow. So the flow just goes past it uninterrupted. And the other thing that we're going to do is we're going to solve this in a kind of stretched coordinate system using Lorentz transformations, and these are quite common things to do in relativity theory. So we're going to stretch the x and y axis in different directions, and then once you do that, you can get an expression for the velocity potential due to our point source in uniform mean flow. And one of the nice things about the Lorentz transformations is that it gives you an expression which looks as close as possible to the no-flow solution. So you can kind of see it there. It looks very similar to the no-flow solution, except that there's an additional phase factor e to the IMX k x bar, and there's a beta squared in the bottom. But apart from that, it looks exactly like the no-flow solution. So having obtained the velocity potential, we want to compute the power. Now, that's a little bit trickier, but fortunately, Harold Levine in 1990 showed that if you have a point source, a singularity essentially, then you can compute the power, the time average power, at a single frequency, I should point out, from the imaginary part of the acoustic field, the velocity potential, evaluated at the source location, multiplied by the source strength. And that's a really elegant thing to do because it avoids any computation of far field intensity. So it just means you need to know the pressure or the velocity potential, in this case, at the source location. So that's really good. And essentially what this is telling us is how much of the pressure is in phase with the velocity potential, with the source strength rather. Because that's what controls the active intensity and therefore the rate of energy production. So now that's the expression for a single source, but of course we have two sources, so the complexity soon kind of builds up. So now if we want to calculate the total power radiation from our two sources, right? So if I want to calculate the total power from the two sources, I need to know the total velocity potential at the primary source location, and that's got contributions from the primary source itself, plus the secondary source, and exactly the same for the secondary source. I need to know the velocity potential at the secondary source location, which includes contributions from itself and the primary source. So now I can just substitute the expression for the velocity potential into this power expression, and then what I get is a quadratic function of the secondary source strength, and then I can find the minimum value of the power with respect to the secondary source strength. And then if I go through that process, it's quite straightforward. It's written up in the paper. Then you can calculate the optimal secondary source strength in terms of the primary source strength via this kind of complex function here. And this is all expressed in terms of a dx, which is d over beta squared, and dy bar, which is dy over beta. And then if you substitute that back into the power expression, you get this expression for the sound power, the minimum sound power due to the presence of the secondary source. And you can see there that there's no explicit dependence on Mach number because it's all kind of wrapped up in the expression of dx bar and dy bar. So we can plot the solution for that. And on the right, what we're seeing here are contours of secondary source position relative to the primary source at the center there for different Mach numbers. So if we look at the solution at 0 Mach number, there's no flow, you can see that it's circular. So as long as you're about 0.1 wavelength from the primary source, you get a sound power reduction of 10 decibels. But as soon as you introduce the flow, you turn up the flow speed, you turn up the Mach number, then your secondary source needs to be closer to the primary source. So what we see there is a couple of interesting things. As you increase the Mach number, you've got to be closer to the primary source to achieve the same level of noise reduction at 10 dB. And then the secondary source needs to be closer to the primary source when you're either upstream or downstream of the primary source. And the other thing is that you get identical power reductions regardless of whether you're upstream or downstream. So that's relatively interesting. But the interesting question now is, how does the secondary source achieve that sound power reduction? Well, we can treat the secondary source strength ratio with the primary source as being a transfer function, because obviously the secondary source is driven from the primary source, so we can treat that ratio as a transfer function here. And if we want to understand how it works, what we need to do is go back into the time domain, and then that gives you the impulse response function of the secondary source in response to a delta function, at t equals 0. Okay? And so you can easily take the inverse Fourier transform, and you get the sum of these two delta functions terms here, and these are appropriately delayed by this time delay here, and that's the time taken for the sound to propagate from the secondary source to the primary source. Another time delay here, which is the time taken for the sound to to travel between the primary source and the secondary source. And you can express these two terms in terms of the angle theta and the distance d. So what does it all mean? Well, so we're going to plot the impulse response function now as a function of t. The impulse response function is literally the response to an impulse at t equals 0. So the primary source is radiating a pulse, an impulse at t equals 0. So what does the secondary source have to do to minimize the power? Well, the first thing it has to do is, well, this first term represents a pulse in negative time. So what that means is that the secondary source has to anticipate the pulse of the primary source at t equals 0. So it knows that it's going to radiate at t equals 0. It needs to anticipate that by this time, and that's the time taken to travel between the secondary source and the primary source. So what that term is actually doing, so the primary source is radiating at t equals 0, and the secondary source anticipates that. It sends a negative pulse, I should add, so that it arrives at the primary source at t equals 0. So that secondary source is loading up the primary source. It's changing its radiation. So as soon as it radiates at t equals 0, it sees a pressure that the secondary source has radiated. Its radiation resistance has changed. It radiates less power. Then once the primary source has radiated less power, There's another term shown here, it's that second delta function, and that's the time taken, that's a pulse, and a delay corresponds to the time taken for sound to travel between the primary source and secondary source. What that term does essentially is to absorb the resultant power from the primary source. So the mechanism is quite subtle. First of all, you change the radiation resistance of the primary source, then you absorb its power. So I think that's kind of moderately kind of interesting. And of course, non-causal response functions are not an issue for single frequency sound because time advances or delays corresponds just to a phase shift. It becomes an issue for random signals that can't always effectively be predicted in the future. So the second subject I want to talk about here is control of the sound radiation from ducts. Now, this was a project that Lars Enkart, who's sitting there, said started 27 years ago, believe it or not. And this was an attempt to try and control actively buzzsaw tones, because we thought this would be an ideal candidate for active control. Buzzsaw tones are tones, obviously, but they're low frequency. So we thought we wanted to see how effectively active control would perform in reducing these tones. So the research objective is to design an array of microphones that could be used to detect the radiation passing through this range of solid angles here. So could we detect the radiation at the duct wall that relates to the sound radiation at the wall? So more formally, can we minimize the integration or the sum of the mean square pressures arranged over this kind of control sector? Now, the answer to that lies in some classic work done by one of my acoustical heroes, Ed Rice, in the kind of late 70s, early 80s. And he showed that if you consider a single mode propagating in a duct, then the wavefronts of these modes with a duct wall propagates essentially at the phase speed, the velocity. So here is a duct mode with the wavefronts propagating at an angle theta mu. M is the azimuthal mode order, mu is the radial mode order. But then, of course, the flow comes in and blows it over. There's a drift. So actually, the kind of energy, if you like, is not at the phase speed, it's at the group velocity. So here's the group velocity angle here. And it turns out that's the important angle because it's also the angle at which a main radiation lobe occurs in the far field. So if a single mode radiates from the end of a duct, get a main radiation lobe, which is at the same angle as this group velocity vector. So essentially, if we can detect the phase speed of the mode at the duct wall, we can infer its group velocity, and we can infer its main radiation angle in the far field. So that's essentially what we're doing. So I'll go through this fairly quickly. So the acoustic field in a duct is the sum of acoustic modes. And what we're going to do now is to write the phase speed of the mode along the duct wall in terms of the free space wave number k and some non-dimensional factor b, which relates to the propagation angle theta. Now, Rice said that if you've got enough modes, you can replace the summation of modes by an integration. So this is the same expression with the summation replaced by an integration. And then what Rice also said was that different modes with the same propagation angle had very similar transmission radiation characteristics. So what we're going to do now, instead of writing the pressure as a function of modal index, we're going to write that pressure amplitude as a function of propagation angle. So now we have an integral where the only quantity that's important is theta, and you'll recognize this as being a Fourier transform, which we can then invert. So once we know the pressure along the duct wall, we can integrate it with this complex weighting function, and we can get the in-duct directivity. So that's essentially a beamformer or a wave number filter, if you like. And I'll go through this kind of quickly. So we can use that idea to sense the sound field inside the duct that relates to one's total sound power. Because what we're going to do here now is we're going to collect this in-duct directivity at a number of axial line arrays on the duct wall, and then we're going to calculate the pressure as a function of theta. We're going to square them, and then we're going to multiply by this bias function, which is a function of propagation angle. And the reason we do that is because we know that modes that propagate with small propagation angle to the duct axis, these are modes that are well cut on, and we know they carry comparatively high sound power in relation for unit pressure amplitude. By contrast, modes kind of here that propagate a high propagation angle to the duct axis, they carry comparatively little sound power for a unit pressure amplitude. So this bias function is kind of shown here, and you can see that it actually fits very well to the actual data. This is real, the crosses are actual data points expressing the ratio of power to pressure, and you can see that it collapses quite nicely on propagation angle. So everything in this problem collapses to a good degree to propagation angle. And this is something that I've come back to quite a bit in my research career. So what we can do then is we can, using this kind of induct sensing method, we can compute something that relates quite closely to sound power. We can drive the secondary sources to minimize that, and then we can calculate the sound power reduction in dB as a function of Blay-tip Mach number. And this dash curve represents the reduction that you get using the induct array compared with the solid line, which is the power reduction that you would get if you could put far-field sensors directly in the radiated field. So if you had perfect knowledge of the radiated power, and you can see that it matches quite well. Now we can follow an identical process, but instead of minimizing power, we use a different bias function that really focuses down on the near cut-on modes, or the near cut-off modes. These are the ones that propagate at high angle to the duct axis, that radiate most strongly to the sideline direction. So this bias function now emphasizes the near cutoff modes, these ones with a high propagation angle. And you can see there, well, you'll see in a moment that it does a good job in controlling the sound radiation radiated at 90 degrees. And again, we can compare the performance of that array with one that obtained by measuring the far field directly, and you can see that it's not too bad. There's a 5 dB penalty as a result of using the induct array compared to the far field array. And finally, in this section, if we arrange our wave number sensor or beamformer to target this range of modes between, say, 20 and 40 or 50 degrees, you can see that we get reductions in the pressure. This is the far field directivity projected onto a sphere, onto a circle, sorry. You get large reductions over this range of angles here, increases out to the sidelines. However, if you start to target now the very well cut-on modes, sorry, the least cut-on modes, then you reduce the mode amplitudes, which large propagation angle, and of course that reduces the sound most effectively towards the sideline directions, whilst increasing the pressure traveling close to the duct axis. The third scenario that I want to consider is something that we've done for quite a long time, probably too long, to be honest, but we keep getting kind of dragged back. And this is the design of leading edge serrations for controlling airflow leading edge noise. Now this work is really the work of Chaitanya Paruchuri, his PhD work probably done, I don't know, 5 or 10 years. And the reason I'm mentioning it now is because at its heart, it uses destructive interference. So one of the things that Chaitanya did was to put a single wavelength serration onto a flat plate, put it into a turbulent flow, and measuring the sound power reduction. So you can see there's the flat plate insert serrations that we used. And the result he found was really quite interesting. So this is the sound power reduction in dB as a function of non-dimensional frequency. In fact, this is a kind of straw hole frequency, FH over U. So this is just the amplitude of the serration relative to the hydrodynamic wavelength, U over F. And what he saw that was really quite interesting is that the noise reductions, or the power reductions, follows this straight line. And that straight line was 10 log 10, FH over U plus 10. And we spent forever trying to understand this result. But it's very robust, been repeated by quite a few labs. And what you can see is that as you increase the serration amplitude, the reduction follows this line until you get to some critical frequency where the self-noise takes over, and then the reductions kind of just fall away. So that's really, really quite interesting. And that is already significant noise reductions of 10 dB at this frequency using a large amplitude leading edge serration. Now, to understand what's going on here, we did an Euler CFD study where we just put a span-wise vortex onto the leading edge serrations, and we looked at the response on the surface. So on the top, you can see the velocity response. On the bottom, you'll see the pressure response as this span-wise vortex passes over the leading edge. Now, I want you to look at the pressure response on the bottom. Unfortunately, I can't. I have to turn the laser pointer on. There we go. Right, so you're just about to see the response on the surface pressure as that span-wise vortex passes over it. Okay. Right, so there's an upwash on the leading part of the vortex. But hopefully what you saw was that you have a kind of a largish pressure response on the leading edge here, but a much greater pressure response at this trough. So it looks like the greatest pressure response of that leading edge serration is concentrated at the root. Now we can exploit that finding by adding two wavelengths together. So if you add two single frequency wavelengths together, you get what we call a double wavelength serration, and that has the effect of introducing two troughs or roots that are displaced in the streamwide direction. So as a turbulent eddy passes over it, it induces two localized pressure responses near that trough location, and there's always a certain frequency where those two streamwise separated sources are 180 degrees out of phase and therefore destructively interfere. So what we're showing now is the power reduction you get due to two single wavelength serrations separately. There it is there. So this is a single wavelength. This is another single wavelength, kind of sort of twice or half the wavelength, if you like. But as soon as you add them together, you get these two roots now, which are separated. You get a much larger sound power reduction. And that's purely because these localized sources at the roots are destructively interfering. So you're using roughly the same edge length, but getting a much larger reduction. Now, Chaitanya pursued that idea even more to try and get even more effective destructive interference between the roots. And so he looked at a whole different family of novel serrations. So starting with the single wavelength serration, then the double wavelength serration, where you have the two roots. And then he looked at the chopped peak, where you just take a sawtooth and you just chop the top off to try and induce a larger pressure response at the root. A slitted root, and then finally the variable slit. So you can see there's sort of a range of slits there of variable length, and then just a single slit. And the results he saw for the sound power reduction spectrum were really quite interesting. So if you look at the single wavelength or the single sawtooth serration, you saw this reduction, which follows that nice line that we saw. And then once you add another single wavelength, you get a double-rooted serration. And now you're getting this additional reduction because of the destructive interference effect. And now, if you look at the slitted peak serration, you can see the reductions are even higher because now what you're doing is matching the source strengths more effectively. But this is really the interesting one. If you have the slitted root, what you're doing there is you're inducing the source strengths to be very closely matched, so that at this non-dimensional frequency of about half, you're getting reductions of 15 dB. Now that is remarkable if you think what we've done here is we've got a kind of turbulent eddies to pass over these serrations to induce almost identical sources that are extremely highly coherent to give you sound power reductions of 15 dB. Now, to get that level of reduction, the coherence needs to be almost perfect, and the sound pressures need to be within about 5% of each other. So to try and arrange that on a single leading edge is quite remarkable, I think. And then, if you look at the slit, you see a similar kind of effect, slightly lower frequency, and then the variable slit has a number of peaks because of the different possibilities for destructive interference. So then what we did is to look in more detail at the slitted profile. Here's some sound power reductions at different speeds. And then to understand the mechanism more carefully, we looked at that Euler calculation more carefully and looked at the vortex response. So it's a span-wise vortex hitting the slitted leading edge. And then what you see is this quite complicated system of secondary vorticity. So the span-wise vortex hits the leading edge, sets up this span-wise vorticity response along the leading edge, and then you have this system of stream-wise vorticity which winds along the edge, hitting the back of the slit. And then if you can see what effect that has on the slits, you can see you get a very localized pressure response near the leading edge and another localized pressure response at the root. And what's happening is that at that tuned frequency is that you're getting very high levels of destructive interference between sources here and sources here. The fourth scenario I want to look at, and I'll go through this quite quickly, I promise, is to look at active control of trailing edge noise. Now, this was a project proposed by Siemens Gamesa, by Steve Buck and Stefan Orlemans, and they invited me to join this project. So the idea is, can we introduce surface pressures near the trailing edge of an airfoil and use that to drive a control system to drive secondary sources to cancel the far-field pressure as an alternative to, say, trailing edge serrations or boundary layer control devices, because that would be quite nice because it would mean there would be no modification to the surface or to the trailing edge. So to understand the feasibility of that process, you only need to look really at a CFD prediction of trailing edge noise. And what you see there is a boundary layer that's become turbulent, really, really chaotic, passing over the trailing edge. And then if you look at the acoustic response below it here, you see what the trailing edge has done is turned the chaos and stochasticity, if you like, of the boundary layer turbulence into something which is very, very well ordered. So the trailing edge, if you like, is almost like acting like a wave number filter. So it's taking all the multiple incoherent wave numbers of the turbulence and filtering it so that only certain wave numbers can radiate. And it was AVIATION back in the kind of 70s and 80s who really described that process extremely well. So if we could arrange for a set of pressure sensors near the trailing edge to do something similar, to act as a wave number filter, to filter out only the components which related to the far-field radiation, that would provide the input to a control system for controlling the far-field noise. Put another way, what we need is a system of trailing edge surface pressures that was coherent with the far-field radiation. Now, this is the airfoil that Steve Buck produced. So what you can see, not very clearly, is there are 64 surface pressure sensors along the trailing edge. There are piezo-ceramic actuators embedded into the surface. And there really is only one research question, is how coherent are these surface pressures near the trailing edge with the far-field radiation? Because if they're coherent, then you can use that as an input to a control system, which will then drive the speakers, which will then produce radiation at the far-field sensors that is coherent with the radiation from the trailing edge. So that's the million-dollar question. Now, we did this test, or rather Steve did this test at the Virginia Tech wind tunnel, and to observe the radiation there, you have to use a beamformer, a microphone array, so it was a 256 microphone array. And this is the beamformer plots, and you can see for the baseline case, and you can see the radiation coming from the trailing edge. There's a bit of radiation from the leading edge. So the bit of analysis that I did in this phase of the project was to see what the coherence would be between the 64 reference sensors near the trailing edge and the beam-formed pressure. Okay. Now, to do that, we measured what's called the multiple coherence function. Now, I'm sure most people are familiar with the single-channel ordinary coherence function, which just tells you the linear relationship between one signal and another signal in the time domain. The multiple coherence is a generalization of that principle. So this says how causally related or how linearly related are these 64 pressure sensors with a beamform pressure. And to do that, you need to do this calculation. And really, this just involves a series, a cross-spectral matrix between each reference sensor and the beamformer pressure, and you have to invert the matrix. And this is all classic textbook signal processing stuff. Okay? And really, the result I wanted to show was this one here. So with those 64 pressure sensors, then we're getting coherence at least 0.5, rising to about 0.7. And I think that's a remarkable result, because what I think this is showing for the first time is a clear causal relationship between the pressures near the trailing edge and the far-field radiation. Now, people will say, well, that's kind of obvious, and it is obvious because it's trailing edge scattering, but I think to show it formally like this, I think is quite a nice result. And then what we could do there, once we have these measured coherences, we could then use it to predict what the far-field noise reductions would be, and I'll show this quite quickly. This is the far-field directivity projected onto a circle. And so if you had a single pressure sensor here, you'd get 13 dB of reduction, a slight increase in noise on the other side where you don't have any actuators. And if you were to spread out the sensors, you'd get kind of 7 dB. And if you spread them out even more, you get about 4 dB of reduction. So what this proves is that active control for trailing edge noise is a feasibility, it's a possibility, even though its source is a turbulent boundary layer. It's a completely feasible concept, and then the project stopped. And if I've got time, I'd just like to tell you that the last piece of work, this is the final bit of work, and it relates to propeller noise synchrophasing. And I've heard a couple of talks already today on this concept. Now, this concept really started about 1980, when it was recognized that if you have more than one propeller side by side, identical, coplanar, co-rotating sources, if you arranged for the blade angle of one to be displaced relative to the other by a fixed separation angle, in this case delta theta naught, then they somehow destructively interfered to give you a net reduction in sound power. Now, I think there must be at least 30 or 40 papers on propeller synchrophasing. And I don't think it's unfair to say that not one of them has really, I don't think, properly explained that mechanism. And I think that's surprising, because actually the mechanism is surprisingly kind of simple, as hopefully I'll show now. So the key to understanding why synchrophasing works for propeller noise is to look at the form of the acoustic field for steady force rotating, or B, if you like, steady forces, one on each blade, rotating around some kind of origin. So here we're kind of showing that here. There's two blades shown here for illustration. We're only interested in considering the radiation from the steady loading due to, say, the thrust or the drag. Now, that steady loading radiates noise. In fact, it generates tones at multiples of the blade passing frequency because that source is accelerating from the relative to the stationary observer. So all this is entirely relativistic. So it's a steady force in the rotating plane, unsteady, or appears unsteady in the stationary reference frame. And so the acoustic far-field pressure is in the form of a sum of blade passing frequencies at harmonics of the blade passing frequency. Now, the key thing, I think, to understanding synchrophasing is to recognize that the complex mode amplitude can be written as a separable function of polar angle. So phi is the polar angle. So that's the polar directivity multiplied by a separate function of the azimuthal angle theta. And the other thing that is really important to recognize is that this term here is simply a spinning mode. It's a pure spinning mode with NB lobes, if you like, which is rotor locked to the rotor, spinning at the same rotation as the rotor, which is why it generally radiates quite inefficiently, because generally it's subsonically radiating. And I think that is the key to understanding how synchrophasing works. So if we look at the form of the acoustic pressure for a single propeller, this is the real part of the pressure. Now we're looking at the acoustic field at the blade passing frequency n equals 1. I'm assuming 4 blades here, and that's rotating at 184 radians per second. And what you see is 4 arms. So what's happening is that the wavefronts are propagating out from the center at the sound speed, but they're also spinning with the rotor, and that has the effect of producing these kind of spiral arms. Now, having this kind of simple form for the acoustic pressure, it's not too difficult to add 2 of them together that are separated by a distance d. Here they're shown separated by d/2 relative to the origin, and we're interested in knowing the pressure outside here. So we simply add the 2 pressure fields together. So not only are they displaced from the origin, but they also have a fixed angular separation distance of delta theta naught. And so the acoustic pressure at the nth blade passing frequency can be expressed like this in terms of the polar directivity of a single propeller multiplied by this azimuthal interference function, phi, which is only a function of the azimuthal angle. Now, you can see that in the general case, it's a bit of a nightmare. It's quite kind of tricky geometry. Now, the mean square pressure, I should say, now we can kind of visualize what effect that has when you take two propeller fields separated by 180 degrees, or rather, I should say, their modal phases separated 180 degrees, so they radiate 180 degrees out of phase. Now, if you take 2 propellers that are quite well separated by 3.4, now I'll explain the significance of this factor in a moment. You can see that you get something which is very similar to the original single propeller sound field, but they destructively interfere when you're 180 degrees above or below it. And in that case, you've got 2 modes, 180 degrees out of phase. The path length differences are 0, and they destructively interfere here and here. Now, if you bring them closer together, you can kind of see that the extent of destructive interference kind of gets better, and the overall noise reduction gets better. And if you bring them even closer, you can see that you get even better noise reduction. And what we're interested in knowing in this last 5 minutes is the extent of the sound power reduction that you get from that process. Now if you take this horrible expression here and you restrict to the calculation to the far field, then you can show quite easily that the mean square pressure can be written in terms of the squared pressure due to the polar directivity multiplied by this interference factor. And in the far field, that interference factor is nothing more than 2 multiplied by 1 plus cosine omega n times cosine sine theta, sorry. Theta is the azimuthal observer angle, plus delta theta n. And so there's only 2 factors which control the azimuthal directivity. The first is this non-dimensional frequency, omega n hat, and that really is just this factor here, which is really the separation distance between the 2 propellers relative to the acoustic wavelength at the frequency of interest. And the second factor is what I'm calling the modal phase angle. So if you've got a mode with NB lobes and you rotate it by an amount delta theta naught, then you have a change in phase by NB delta theta. So it's just those 2 factors that control the directivity. The question is, this is a very, very simple theory, but these results here are essentially exact. Okay, there is no approximation gone into them at all. So the question is, how well do they fit the data? Well, extremely well. So this is some azimuthal directivities measured in a recent paper by NASA, by Schiller, and the red circles represent the measured directivity, and these solid lines represent the predicted directivity from that simple expression I showed you. And you can see that the agreement is within 1 or 2 dB. Very, very good. And we can also compare with some recent CFD data obtained by Barakos, unpublished data, and this is for a 3-bladed propeller. You can see the relative phase angles shown here. And you can see that the agreement is almost perfect. And it's perfect because the original expression for the far-field directivity is an exact expression, because the form of the sound field in the azimuthal direction is an exact result. So the form of the pressure really is in the form of a single spinning mode locked to the rotor. And it must be that to generate single frequency sound. So these are exact expressions giving quite good agreement. So very, very quickly then, we're interested really is the total radiation. So what we can do is we can just integrate the far-field intensity over a sphere, but because this mean square pressure is separable, we have one integral over phi. Now that is just the power due to a single propeller, another integral over theta, and what's nice is that this integrates quite neatly to this expression here, involving a Bessel function, J0, a Bessel function with argument equal to that non-dimensional frequency, multiplied by cosine delta theta n, which is the modal phase angle. And you can kind of, so the ratio of the power due to synchrophasing relative to the power due to a single propeller is just this expression here. And then you can kind of plot that. So this is the power reduction versus frequency along here and phase angle there. And you can see that at the optimal phase angle, you're getting kind of very, very good levels of reduction. And finally, my last slide, I promise, or penultimate slide, then what you can do is you can take this expression and you can expand it using small angle approximations, because we're only interested in this expression for small values of omega, where the propellers are quite close relative to the wavelength, and for delta theta of about pi, where the modal phase angles are 180 degrees apart. And so you can expand this as a series expansion like that, and it fits the data quite well, obviously. But then if you evaluate this expression at the optimal phase angle, this term here disappears. And what this tells you is that the power reduction due to two propellers at the optimal phase angle is just a half times omega n squared. And really, this is the ratio of power you get from going from a monopole to a dipole. So that's essentially what we've done. So a single propeller radiates with monopole efficiency. You bring two close together at the optimal phase angle, it radiates with kind of dipole radiation efficiency. So I think that's kind of an important result. So really, the only thing you need to know is how close your propellers are relative to the acoustic wavelength. And that's it, and you can generalize this approach. This is the power due to two propellers. If you've got n propellers, then all you need to do is to calculate the power due to all the different combinations of propeller. And so you can kind of generalize the result. And very exciting, on Wednesday, I'm going to propose an algorithm for identifying these optimal phase angles for minimizing the sound power. So that is my talk. So thank you for listening. I appreciate it's been a long day. So thank you for listening, and